Okay, section 5.2, we're going to talk about one-to-one functions and inverse functions. So a function is said to be one-to-one if for any two different inputs, so two different x's, if we get two different outputs or y values. That's to say that if we had if two different x's, so x1 and x2, when we put them into our function, so f of x1 does not equal f of x2. Again, no y is duplicated whatsoever in this function. So if we were to look at this one that has your age and the corresponding cholesterol, notice that if you are age 55 or 61, they both had a cholesterol reading of 38. Because they have the same value in our range, this is not one-to-one. And knowing if a function is one-to-one is important because we cannot get inverses unless your function is one-to-one to start with. So if we take a look at this function, that's just a series of points, are any y values repeated? They're not. So this one is a one-to-one function. One-to-one. That's all we're checking for. We can also check for this graphically by doing what's called the horizontal line test. And the horizontal line test simply says, if you draw a horizontal line, do you intersect your graph in two different places? So we've got two different graphs here going. So I've gone ahead and graphed y equals x squared, which is just our parabola. If I were to draw a horizontal line, notice that I would intersect my function in two different spots. There are the same y value have two different x's. That is not acceptable. So this one would not be one-to-one. If I look at my cubic parent function here, so I've got this cubic function. If I were to graph this and do a horizontal line, nowhere do I intersect in 2 points. So this function is one-to-one, which is what we want. Okay, let's turn over to the next page. What does this all mean? Okay, so inverse functions are important because sometimes we want to use the output and figure out what the input is. So for instance, if we have population and years, so we know each year what the population is, if I knew the population, I could work backwards to figure out the year. So that's called inverse. So suppose function f is a one-to-one function. The correspondence going from the range, so my y values of f, back to the domain of f is called the inverse function. And the way we designate our inverse function is we use the same letter of our function, so f, so this case would be f. To show that it's an inverse, we put this -1 up in the exponent position. It's not really an exponent. It is telling us that the inverse function of f is, and then would have, whatever that function is. But it lets us know that whatever we write here is the inverse of function f. So for instance here, if I have this function that gives me, if I have a state, the function, so let's call this function f here, the function gives me the population. And it maps it like that. So if function f gives me this, if I input a state, it gives me the population. F inverse is going to take the population and give me the state. So for instance, if I said the population was 6.2 million, F inverse is going to tell me that that must be Indiana. If I tell my inverse function that the population is 6.1, it's going to tell me that the state must be Washington. So it gives us back what we originally started with over here. Likewise, if we said the population was 0.8 million, my inverse function would say, well, the state must be South Dakota then. And that would be true for every state here. Okay, so again, our inverse function gives us back what we started with. If we had a set of points such as this, my inverse function It takes whatever was a y value, and it makes it the x value, and it takes the x value, and that becomes the y value for the inverse. So my original function, this is function f right here, if I put a -5 in, I got a 1 back. If I put that 1 into the inverse, I get a -5 back. If I put 3 in, I get 3, so that's not so interesting, same with zeros. If I put a 2 into my original function, I got a -4. Now if I take that -4 and put it into the inverse, I need to get back to the original value, which is 2. And likewise, if I take -8 and put it into the inverse, I should get a 7 out of that. So the inverse just switches the x's and the y's, or switches the domain and the range. The domain of my inverse, so this is f inverse, is as follows. So the domain for my inverse function is a set of all the input values. So 1, 3, 0, -4, and -8. The range of the inverse was all the y values here. So -5, 3, 0, 2, and 7. And notice that the range of my inverse is the same thing as the domain of the original function, and vice versa. That's all this is saying. Here's the inverse of f times f of x equals x, as long as x is in the domain of f, and as long as x is in the domain of f inverse. Okay, so what we want to do now is we've given you a function g of x, and I've given you g inverse of x. Let's blow this up a little bit. And we want to verify that these really are inverses. The way we verify this, or prove this, is I need to show that g of g inverse of x equals x, and I need to show that g inverse of g of x equals x. So I've got to do both of these things. So let's start with this one. G inverse says I'm going to take x and take the cube root of it. So now I'm going to take that cube root of x and put that into function g. So that is now my input. Function g says take the input and cube it. Well, cubing a cube root, they cancel each other, so we're left with x. So yes, I proved that g of g inverse of x equals x. And now I'm going to do the same thing in the opposite order. So if I compose g inverse with g of x, I want to see if that equals x. So g inverse of x cubed, I'm now taking x cubed and putting that into g inverse. So x cubed, I want to take the cube root of that. Cube root of cubed cancels, leaving just x. X does equal x. So we've proven that g and g inverse are inverses of each other. Now let's just try it with another one. Okay, so got a new function, function f this time. And I've got to prove this by saying f of f inverse of x, does that equal x? And likewise, does f inverse of f of x equal x? So we're going to do it both ways. So let's do this first one. F inverse says 1/2 times x minus 3, and I'm putting all of that into f. F says 2 times that amount, so 1/2 times x minus 3, and I still have to add 3 to that. Okay, this looks messy, but let's go ahead. 2 times 1/2 x, I'm distributing the 1/2, minus 3/2 plus 3. I now multiply 2, or distribute this in here. 2 times 1/2 is 1, so I just have an x. 2 times negative 3/2 gives me a negative 3, plus 3. Well, the negative 3 and positive 3 cancel each other, so I've just got x equals x. Excellent, that is proven. Let's go to the next video now to finish off this proof.